Now look at practice question set number 20. It's a Michelson experiment, a rotating mirror experiment where light strikes one side as the mirror rotates, comes back, and makes 1/8 of a rotation during the time that it takes the light to travel that return distance. We know how to deal with these, right? We always deal with them exactly the same way. We write down two equations. What are the two equations that I would write down in any Michelson experiment, Parker? Good. V equals d over t, and somebody said, Mateo, I think, said t is equal to 1 over f. Good. Anna, what does little t stand for there? No, little t isn't the period. Yep. I'm sorry? Okay, it would be the time for 1/8 of a rotation of the mirror, because in the end, the mirror makes 1/8 of rotation during the time that it takes the light to go from here to here and then back to here again. It has to have made 1/8 of rotation. So it also corresponds to the time that it takes the light to travel that distance. What does big T stand for? Anna? The period. That's the time for one complete rotation, right? Now, when you solve for something, and that's the next step, right? Sub in your numbers and solve for something. That something will be one of two things. What are the two possibilities that I'll solve for in the next step? Big T, little t. I don't know which one it's going to be. I don't know which one it's going to be until I start subbing my numbers in, and that's okay. I solve for one of them, and then I get the other one, because the one that I get is, ironically, never the one that I actually want. Get the other one, and then sub it back into the other equation and get what I'm looking for here. Okay, let's start subbing numbers in. We know the speed of light. The accepted value is 3 times 10 to the 8 meters per second. We have to use that because we're looking for frequency. We need a speed, and that's the only speed we have, 3 times 10 to the 8. The distance here is 60,000 meters, or 60 kilometers, divided by the time for 1/8 of a rotation. 60,000 divided by 3 times 10 to the 8 is 2.00 times 10 to the negative 4 seconds. So we solve for little t. That's fine. It's not what I want, though. Then if I got little t, what do I actually want? Big T. And how do I get big T from little t? Times it by 8. If it was a 6-sided mirror, we would times it by 6, or a 12-sided mirror, we would times it by 12. Okay, this gives me big T, which is 1.6 times 10 to the negative 3 seconds. Now we're going to sub that into there. 1.6 times 10 to the negative 3 seconds equals 1 over f. How do you solve for frequency now? 1 divided by 1.6, right? F goes up, 1.6 goes down, end up basically just swapping places. And when I do that, I believe, pretty sure it works out to be 625 hertz, or 6.25 times 10 to the 2 revolutions per second. We've said now for a couple of days now, or yesterday at least, we said that the frequency is typically 10 to the 2 hertz, not always. Hey, we don't know for sure that B, C, and D are wrong when I look at it, but there's a better chance of A being the correct answer than there is B, C, or D, because A is the only one that's 10 to the 2 hertz. So if I get 10 to the 2 when I solve it the way that I think is correct, odds are I've done the question correctly. If I got D, it doesn't mean it's wrong. If I get D when I solve it this way, it doesn't mean it's wrong, but it is probably worthy of checking your work, because it's not usually going to be that high for a frequency. All right? Question number 2. We got some information here in the box, and it's for 2 questions. The first question says, one difference between radio waves and visible light is that can radio waves be reflected? Sure, why couldn't they? Okay, that's not a correct answer. They can be reflected. Any type of EMR can be reflected. Can they travel through a vacuum? Yeah. Sure they can. They better be able to. Otherwise, NASA would have a tough time communicating with spacecraft that they send out there. Okay, the vacuum of space wouldn't carry radio waves. The radio waves travel at a lower speed. No, they travel at 3 times 10 to the 8, just like visible light and any other type of EMR. So it must be D, but let's just double check that. Do radio waves have a longer wavelength? Radio waves have a smaller frequency. And if they have a smaller frequency, they must have a longer or bigger wavelength. So D is the right answer, yeah. And number 3, which also goes with this, says radio waves from space longer than 1/10 the diameter of the radio telescope. The diameter, they tell us up here, is 305 meters. So they're telling us here that the wavelength is 30.5 meters, right? The radio waves that are this length, 1/10 the diameter. So the wavelength is 30.5 meters. We want to look for the frequency of the waves. Lambda, looking for F. Is there anything else that we actually have here? Yeah, the speed of light, V or C, which is 3 times 10 to the 8 meters per second. All we're going to do now is say V is equal to F times lambda, or F is equal to V or C over lambda. 3 times 10 to the 8 divided by 30.5. That's going to give me C. Now, in period 1, when I went over this in period 1, we were able to pretty much guess that the answer was C. How? 10 to the 6 is radio waves. 10 to the 9 is microwaves. 32 is also radio waves, an extremely low frequency radio wave, 10 to the 1. And technically, I suppose 10 to the minus 7 would be as well. Although you'll never see EMR that's 10 to the minus something hertz. 10 to the minus something meters for wavelength? Yes. 10 to the minus something hertz? No. The EMR is always going to be 10 to the positive hertz. It's not going to be D because that's microwaves. Could be B because that's radio waves, but not likely. Not likely going to be that small. C is by far the most probable answer. 10 to the 6 falls nicely in the middle of radio wave range, and as it turns out, it is the answer. 4. Which of the following types of radiation has the longest period? I don't know. Figure it out. If we want a big T, then we need a small f because it's on the bottom, right? Which one has the smallest frequency? Radio waves. And 5, an ice rink is lit by bluish light. There's a wavelength of 500 nanometers. What's the period? I was going to say 500 times 10 to the minus 9 meters. Somebody said for another question, we know what the speed of light is. It's 3.00 times 10 to the 8 meters per second. What do you want to try? Nicole, what do you want to try first here? Or second, whatever. Got an idea for any part of this question? Okay, let's try V is equal to F times lambda, or C is equal to F times lambda. We have lambda, we have V, so let's solve for F. Okay, that works. Because it's 3 times 10 to the 8 divided by 500 times 10 to the minus 9. And that's going to be 6.0 times 10 to the 14. Is that right? You know what? Nicole's off the hook now. T is equal to 1 over F. 1 over 6.0. And I think that one gave me A, wasn't it? 1.67 times 10 to the minus 15. Finally, numerical response, question number 1. An explosion produces a flash of light at a distance of 6.06 kilometers from a group of people. How long does it take to reach the people? Man, don't make this one harder than it has to be. Say V equals D over T for this, right? T is equal to D over V. D is 6.06 times 10 to the 3, or 6,060, divided by 3 times 10 to the 8. Gives me a time of 2.02 times 10 to the 5. 10 to the negative 5, you're right, thank you. If it was 10 to the positive 5, like that would be ridiculously far away, right? Because light travels so fast. It is 10 to the negative 5. So it becomes 2.2025. 2025. Let me